On a clear day in southern Spain, you can see Africa from the shore. The Moroccan coastline sits just 14 kilometers across the Strait of Gibraltar. That is less than the distance across the English Channel at its narrowest point, and the English Channel has a tunnel under it. So the question seems almost too obvious to need asking. Why is there no bridge or tunnel connecting Europe to Africa? The distance is short. The technology exists. The economic benefit would be enormous. 2 continents, billions of people, connected by a crossing, you could drive in minutes. The idea has been studied, proposed, and discussed for over a century. Spain and Morocco signed a formal agreement in 1980 to explore the crossing. Studies have been commissioned. Engineers have drawn plans. Politicians on both sides have expressed support at various times, and yet nothing has been built. Nothing is under construction. Nothing has even reached the stage of serious funding commitment. The reason is not political will, not primarily. The reason is what lies beneath the surface of those 14 kilometers of water. A geological situation so hostile to engineering that it has defeated every serious proposal so far, and may defeat every proposal for decades more. This is the story of why 14 kilometers of water has stopped 2 continents. To understand why Gibraltar is so difficult, start with why the Channel Tunnel succeeded. The English Channel looks intimidating, rough seas, busy shipping lanes. The tunnel is 50 kilometers long, far longer than the Gibraltar crossing would be. It cost £15 billion and took 7 years to build, but it worked. And the geology is the reason. Under the English Channel lies a layer of chalk marl, a soft, consistent, relatively impermeable rock that extends the full tunnel length. Tunnel boring machines could cut through it predictably. The chalk marl does not shift significantly. It does not flood easily. It holds its shape after excavation without elaborate support. Engineers knew exactly what they were drilling into for every kilometer. The geology was the tunnel's greatest asset. Gibraltar is the opposite of this in almost every way that matters. The strait sits at the boundary of 2 tectonic plates. The African plate and the Eurasian plate meet almost exactly under this water. The boundary between them is not a clean line. It is a zone of complexity, fractured rock, fault lines running in multiple directions, sections of seabed moving at different rates relative to each other. The geology changes dramatically over short distances. What works for 100 meters might be completely different for the next 100. Predicting what a tunnel boring machine will encounter is extremely difficult. And when what you encounter is unexpected fractured rock under the sea, the consequences are not merely inconvenient. They are potentially catastrophic. The second fundamental problem is depth, and it is more severe than most people realize. The Strait of Gibraltar is 14 kilometers wide at its narrowest point, but the depth in that narrowest section reaches 300 meters. For comparison, the English Channel at its tunnel crossing is about 75 meters deep. The Gibraltar seabed drops to depths 4 times greater than the channel. This matters enormously for both bridge and tunnel options. A bridge at 300 meters water depth would require foundations of extraordinary scale. The deepest bridge foundations ever built reach about 80 meters below water. Extending that to 300 meters is not a linear engineering challenge. It is a qualitative leap into territory that has never been attempted. The forces on such foundations from waves, currents, and ship impacts would require structures of unprecedented size and cost. The shipping traffic through Gibraltar makes the challenge even more severe. This is one of the busiest shipping lanes in the world. Over 100 ships pass through every single day. Massive container ships, supertankers, military vessels. A bridge must provide enough clearance for all of them to pass underneath. That means the bridge deck must be at least 65 meters above the water. Combined with 300 meters of water depth below, the towers would need to be enormous. The main span would need to be several kilometers to avoid placing foundations directly in the shipping lane, where anchors and ship impacts are constant risks. No bridge with a span of this length and tower height has ever been built. The current longest bridge span in the world is about 2 kilometers. Gibraltar would require a main span approaching 5 kilometers. More than twice the longest ever constructed, in far more hostile conditions. Even if the geological and depth challenges could be solved, another force waits. The current through the Strait of Gibraltar is extraordinary, not just surface current, a layered system of currents moving in opposite directions. At the surface, Atlantic water flows eastward into the Mediterranean. The Mediterranean loses more water to evaporation than it receives from rivers. It becomes saltier and denser than the Atlantic. This dense, salty water sinks and flows westward along the bottom, back out into the Atlantic at depth. The result is a 2-layer current system flowing in opposite directions simultaneously. The surface current runs at 3 to 4 knots eastward. The deep current runs westward beneath it. This bidirectional flow creates complex turbulence at the boundary between layers, and it creates sediment transport that continuously reshapes the seabed. Any structure placed on the bottom of the strait must resist both currents, and must be designed for a seabed that is not static, that moves over time. Submarine cables crossing the strait require regular inspection and maintenance specifically because the strong currents shift the sediment around them. A tunnel on the seabed, or foundations for a bridge, would face similar dynamics. Scour, the erosion of sediment from around a foundation, is a major concern. Strong currents accelerate around obstacles and remove material from beneath them. Foundations that seemed solid when installed can be undermined over years. The current through Gibraltar is not an occasional storm event. It is a permanent feature of the geography, present every hour of every day. For the lifetime of any structure built there, the tectonic plate boundary under Gibraltar adds a threat that towers above all others: earthquakes. The region has a documented history of significant seismic events. The 1755 Lisbon earthquake, one of the most powerful ever recorded in Europe, originated near this plate boundary and killed tens of thousands of people. The earthquake generated a tsunami that devastated coastal areas across the region. Waves reaching 30 meters struck the Moroccan and Portuguese coasts. This was not a unique event. The region experiences regular seismic activity. Smaller earthquakes occur frequently. Major events happen on geological timescales. Any structure crossing the strait must be designed to survive these events. For a tunnel, the challenge is designing a structure that flexes with ground movement, without losing integrity, without flooding, without collapsing. The Channel Tunnel in the relatively stable English Channel required careful seismic design. A tunnel under Gibraltar would need seismic design of a completely different order. For a bridge, earthquake design at this scale has no precedent. The tower foundations would need to survive ground movement in fractured seabed rock, while holding up a deck 65 meters above the water, carrying vehicles and trains, and doing so repeatedly over a design lifetime of a century or more. Seismic design for bridges has advanced enormously in recent decades. Modern cable-stayed bridges in seismically active zones perform well in earthquakes, but the scale and geological complexity of Gibraltar is beyond any tested application. Engineers can calculate what a structure needs to survive a given earthquake. What they cannot easily do is predict what earthquakes will occur at a tectonic plate boundary over the next 100 years. Designing for the worst plausible event requires assumptions about events that have not occurred in the historical record but are geologically possible. The most credible proposal on the table for decades has been a rail tunnel, not a road tunnel. A dedicated rail link between Spain and Morocco. The concept involves a tunnel descending from both shores at steep angles, down to a depth of around 300 meters at the center. Two single-track tubes side by side, with a central service tunnel between them. Similar in concept to the Channel Tunnel, but far deeper and far longer. The total tunnel length under this design would be approximately 38 kilometers, including the approach sections on both sides of the actual strait. The geological surveys conducted over decades have identified possible routes, trying to find sections of the seabed with more stable rock conditions, avoiding the worst fault zones, looking for coherent rock formations. The results are not encouraging for simple engineering. The rock under the strait is highly variable over short distances. What begins as workable material can transition to fractured unstable zones, without warning that a survey from the surface can reliably predict. Cost estimates for such a tunnel have ranged widely, from 5 billion euros in optimistic early studies, to over 15 billion in more realistic recent assessments, and experienced tunnel engineers suggest even these numbers may underestimate the challenges of working at 300 meters depth in difficult geology. The Channel Tunnel final cost was roughly double its original estimate. A Gibraltar tunnel would likely face similar or greater cost overruns, given the geological challenges that no survey can fully characterize in advance. Assume for a moment that the engineering challenges could be solved. Would the crossing actually generate enough traffic to justify the cost? This question has been studied almost as thoroughly as the geology, and the answers are more complicated than the enthusiasts for the project suggest. The current traffic between Europe and Africa crosses by ferry. The Algeciras to Ceuta ferry takes about 35 minutes. Several million passengers use it each year. A tunnel or bridge would be faster, perhaps 10 to 15 minutes by rail. But the question is, how many additional passengers would the crossing attract? Beyond those already using the ferry, most analysis suggests a fixed link would attract significantly more traffic. Tourism from Europe into Morocco would increase substantially. Trade in goods would benefit from reliable all-weather rail access. Agricultural produce from Morocco reaches European markets faster, industrial goods move more reliably than by ferry in winter storms. The broader economic development argument is also made regularly. A fixed link would integrate the Moroccan economy more deeply with Europe, enabling supply chain development and investment that ferries cannot support. These arguments are plausible, but they rest on projections that are uncertain. The experience of other fixed links shows that traffic forecasts are often optimistic. The Channel Tunnel consistently carried less traffic than original forecasts predicted. For years after opening, it struggled financially. It eventually became viable. But the timeline was far longer than investors expected. A Gibraltar crossing would face the additional challenge of crossing a cultural and economic boundary far more significant than the English Channel. Not just geography, but regulatory systems, customs procedures, and political relationship, all of which affect how many people and how much cargo actually use the crossing. Even if engineering and economics supported the project, politics adds another layer. Spain and Morocco have a complicated and sometimes tense bilateral relationship. The Spanish enclaves of Ceuta and Melilla sit on the Moroccan coast. Morocco considers them occupied Spanish territory. Spain considers them integral parts of Spain. This dispute has never been resolved. It generates periodic diplomatic friction. A tunnel or bridge between the two countries would require unprecedented cooperation, agreeing on construction standards, on operational management, on revenue sharing, on customs and immigration procedures at both ends, on security arrangements for a structure that would become a critical infrastructure target, on what happens to the crossing if the bilateral relationship deteriorates. The Channel Tunnel required the United Kingdom and France to solve similar questions. Two countries with a generally cooperative relationship and shared EU membership. They found solutions, but the negotiations were difficult and took years. Spain and Morocco face the same negotiating challenges with a more complex backdrop. The European Union is also relevant. Morocco is not an EU member. A rail tunnel connecting EU territory to non-EU territory creates customs implications. Every train crossing would need to manage the EU external border. In a tunnel 38 kilometers long where stopping in the middle is not an option, the border management logistics alone require significant infrastructure on both ends. None of this makes the crossing impossible, but it adds costs and complexity. That must be solved alongside the engineering, not instead of it. For a Gibraltar crossing to become reality, a specific sequence of events is required. First, a definitive geological survey more detailed than anything done so far. Multiple deep boreholes, extended seismic monitoring, comprehensive rock sampling. Building a picture of the geology that is accurate enough to design for reliably. This survey alone would cost hundreds of millions of euros and take years. It would need to be funded jointly by Spain, Morocco, and the European Union. Second, an engineering design that addresses the specific conditions identified. Not a generic tunnel concept, a detailed design for the actual geology found, with realistic cost estimates based on those specific conditions. Third, a financing structure that can support a project of this cost and risk. No private investor would fund a Gibraltar tunnel without substantial public guarantees. The risk of cost overruns and lower than forecast traffic is simply too high. Public funding from Spain, Morocco, and EU institutions would be essential. Fourth, a bilateral treaty between Spain and Morocco covering all operational aspects: governance, revenue, security, border management, maintenance responsibility. A treaty stable enough to survive changes of government in both countries. Fifth, resolution or at minimum management of the Ceuta and Melilla dispute. Not necessarily a final solution, but a framework that allows cooperation to proceed. Each of these steps is individually difficult. All of them together, in sequence, is a political and institutional challenge that has defeated every previous attempt to move the project forward. The engineering is the most tractable part of the problem. Everything surrounding the engineering is harder, so why is there no bridge or tunnel between Africa and Europe? Not because of distance. 14 kilometers is nothing by modern standards, not because of technology. We have the tools. In principle, the water is too deep for proven bridge foundations. The geology is too unpredictable for confident tunnel planning. The currents are too strong, and the seismic risk too significant to design confidently for the lifetime of the structure. The costs are too uncertain, and the traffic forecasts too unreliable to attract private financing without unprecedented public guarantees. And the political relationship between the two countries has never been stable enough for long enough to carry a project of this duration. These barriers are not permanent. They may be overcome. Technology improves. Political relationships evolve. Floating tunnel concepts are being studied that might work at 300-meter depths. If climate change increases the value of land routes as shipping patterns shift, the economic case might strengthen. If Spain and Morocco resolve their territorial disputes, the political foundation for cooperation might become more solid. None of these things are impossible. They are simply not current. The crossing that looks so obvious from the shore at Gibraltar is hiding an extraordinary concentration of engineering, geological, economic, and political challenges beneath its 14 kilometers of water. The strait that divides two continents is narrow in distance, and enormous in everything else. If this changed how you see that gap on the map, leave a comment below. Tell me which impossible engineering project you want explained next. Like and subscribe. New engineering stories every week. One proposed solution avoids the depth problem entirely. The submerged floating tunnel, also called an Archimedes bridge in some engineering literature. The concept is fundamentally different from either a surface bridge or a seabed tunnel. Instead of resting on the bottom or spanning across the top, the tunnel floats at a fixed depth below the surface, perhaps 30 to 50 meters down, deep enough to avoid ship traffic and surface wave forces, shallow enough to avoid the extreme pressures of the seabed at 300 meters. The tunnel is buoyant. It naturally wants to rise to the surface. Tethers anchored to the seabed hold it down at the design depth. The structure is essentially suspended in the water column. Neither a bridge nor a conventional tunnel, something in between. This design solves the depth problem completely. No foundations need to reach 300 meters. Only the tether anchors do, and anchor systems for deep water are well understood from offshore oil platforms. Norway has studied this concept intensively for crossing its deep fjords. Several Norwegian fjords are too deep and too wide for conventional bridges or tunnels. The floating tunnel is the only engineering option that works at their scale. Norway has proposed pilot projects to develop and test the technology. None has yet been built anywhere in the world. The concept remains unproven at scale. The main engineering concerns center on dynamic loads. Currents push the tunnel sideways. Tethers resist this movement, but under varying current speeds and directions, the tunnel could oscillate, building up resonant vibration in the structure over time. The same phenomenon that destroyed the Tacoma Narrows Bridge in 1940. Designing a floating tunnel that is aerodynamically and hydrodynamically stable across the full range of conditions at Gibraltar is a serious technical challenge, but it is a challenge being actively worked on by Norwegian and other engineers. The floating tunnel concept may be the key that eventually makes Gibraltar possible. Not in this decade, but perhaps in the one after. It helps to compare Gibraltar with crossings that were actually built. The Øresund Bridge and Tunnel connecting Denmark and Sweden opened in 2000. It is 16 kilometers long, slightly longer than Gibraltar at its narrowest. Water depths on the Øresund crossing reach about 8 meters, not 300. The geology is stable sedimentary material suitable for tunnel boring. The two countries had cooperative bilateral relations and shared EU membership. Traffic forecasts were credible based on existing ferry traffic between major cities. Every factor that makes Gibraltar difficult was favorable on the Øresund. The result was a project that was expensive but manageable and successful. The Fehmarnbelt Tunnel between Denmark and Germany, currently under construction, will be the world's longest immersed tunnel when complete. About 18 kilometers, maximum depth around 40 meters. An immersed tunnel is built differently from a bored tunnel. Large concrete tube sections are prefabricated in a dry dock, floated into position over the prepared trench in the seabed, then sunk and joined together to form a continuous tunnel. At 40 meters depth, this is feasible. At 300 meters, it is not. Water pressure on an immersed tunnel section at 300 meters would be enormous. The structural requirements would make each section prohibitively heavy and costly. The Fehmarnbelt crossing illustrates the ceiling of current immersed tunnel technology. Gibraltar sits far beyond that ceiling, in a completely different engineering regime. The crossings that have been built share common characteristics: shallow water, stable geology, cooperative neighboring countries. Gibraltar has none of these. That is not a coincidence. It is why it has not been built. There is a useful parallel case closer to Gibraltar: the Strait of Messina, the narrow water between mainland Italy and Sicily. At its narrowest point, Messina is only 3 kilometers wide. Italian governments have proposed a bridge across it for over 50 years. Studies have been commissioned, designs have been approved. Construction contracts have been awarded and then cancelled. Funding has been committed and then withdrawn. As of today, no bridge exists. The crossing is still made by ferry. The reasons are instructive. Messina sits in a seismically very active zone. Major earthquakes are regular events. The 1908 Messina earthquake killed over 200,000 people. Designing a bridge to survive the worst credible earthquake here is extremely demanding. The wind conditions in the strait create aerodynamic challenges for a long-span bridge, and the political economy of southern Italy has made sustained commitment to mega projects difficult. Messina is only 3 kilometers wide, Gibraltar is 14. If a 3-kilometer bridge in a seismically active strait has not been built despite 50 years of political discussion and multiple committed funding cycles, it puts the Gibraltar challenge in useful perspective. Not every engineering project that seems possible actually gets built. The gap between technical feasibility and actual construction is filled with economics, politics, geology, and institutional capacity. Gibraltar has more of each type of barrier than Messina, and Messina is still waiting for its bridge after half a century of trying. There is one more dimension to this story that deserves attention: what the crossing would actually mean if it existed. Europe and Africa are separated by history and economics as much as by water. Sub-Saharan Africa has the fastest growing population on Earth. Europe has an aging population and significant labor shortages in key sectors. The economic complementarity between the two continents is enormous and underutilized. A fixed crossing at Gibraltar would not by itself change this relationship. The deeper barriers to African-European integration are regulatory and political, visa requirements, trade barriers, investment frameworks, education access. None of these would be solved by a bridge or tunnel, but infrastructure has a way of pulling other changes behind it. The Channel Tunnel changed the relationship between Britain and continental Europe in ways that extended far beyond simple travel time reduction. Business relationships deepened, tourism patterns shifted. A generation grew up thinking of Paris as a train ride rather than a foreign country. A Gibraltar crossing might do the same for the relationship between Europe and Morocco, and perhaps eventually for a broader European-African connection. The engineering challenge is real and severe, but it is worth remembering why it would be worth solving, not just to save 35 minutes on a journey, but to make two continents feel, over time, a little less separated. That is a reason to keep studying the geology, keep running the economic models, keep looking for the engineering solution that the strait has so far resisted. The 14 kilometers of water at Gibraltar is a small distance with a very large meaning. The geological surveys done so far have revealed one more uncomfortable truth. The seabed of the Strait of Gibraltar is not stable on geological timescales. The African plate continues to move northward at roughly 4 millimeters per year. Over a century, this movement accumulates to 40 centimeters. Over the lifetime of any major infrastructure, the plates have moved measurably. Any fixed structure crossing the boundary between them must accommodate this drift. The Channel Tunnel crosses stable geology. It barely needs to worry about plate movement. A Gibraltar crossing would be anchored to two pieces of ground moving toward each other. The design implications are significant: expansion joints, flexible connections. The crossing must work today, and still work in 100 years when the geometry has changed. This is not an insurmountable problem. Engineers design for plate movement elsewhere, but it adds another layer of complexity to an already extraordinarily complex project. Every layer of complexity adds cost, and uncertainty, and time.